scattering of non-relativistic particles. So, suppose we consider a scattering center, symmetric scattering center, spherically symmetric scattering center. That means the scattering potential VR is only dependent on VR, not depend on theta, not depend on theta or phi. So it's a spherically symmetric central potential. It's a scattering center. Now, suppose you allow to pass some free particles towards the scattering center, and obviously due to this obstruction in the path of the free particles will scatter away like that. And it is found in the very historic scientific experiment, namely Rutherford-Goldfoil experiment. In Rutherford-Goldfoil experiment, the scattering center was nucleus, okay, atomic nucleus. That means nucleus of the gold atoms. Similarly, in a general note, we have considered a spherically symmetric potential to be the scattering center. So this is a scattering center, and some collimated beam of free particles, they are allowed to pass around this scattering center, and as a result, due to this obstruction in the path of the free particles, will scatter away like that. And if you think it in the classical mechanical way, if you consider the ideas of classical mechanics, then you will find there will be no scattering but scatter particle along this direction, because it is directed in the very opposite portion of the scattering center. So classically there will be no scatter particle in this direction. But if you consider it in quantum mechanics, any free particle can be considered as the plane progressive wave, okay, plane waves. And waves can penetrate, waves can overcome this barrier, and you may still find some light or some waves in this direction. So in quantum mechanics and in classical mechanics, the interpretation of scattering should be slightly different. Okay, in quantum mechanics, you can solve the Schrodinger equation for this potential. Then you could find the probability of having the scatter wave in this portion. Okay, so that will be somehow different from the classical interpretation. So in these classes or in some series of classes, today's class and the next classes also, we have discussed about the features or some speciality of such scattering of non-relativistic particle in the light of quantum mechanics. Okay. So now try to construct the problem in a very uh, meaningful way, or in a very specific way, so that we can develop the mathematical tool to study the features of this scattering in such condition. Okay. So we have considered this scattering center, okay, and set some collimated beam, which is free particle, the beam of free particles to be incident on this scattering center. So this is the incident ray, and after this incidence they will scatter away like that, and these are the scatter wave. So phenomenologically, you can say that. So phenomenologically, you can say that the total wave function of the system, complete wave function of the system, psi, that will be the superposition of the incident wave and the scattered wave. So this is psi I plus psi s, superposition of the incident wave and the scattered wave. And as per our setup, we have considered the incident wave as the beam of T particles. So that's why in the words of quantum mechanics, it will correspond to the plane progressive wave, and any plane progressive wave can be demonstrated by the trivial form of wave function e to the power I k dot. So psi I, this is e to the power I k dot. Now come to the scattered wave psi s. So scattered wave will not be the plane progressive wave, because due to this obstruction, the nature of the wave front of the incident wave will be altered. Okay. Initially it was plane progressive wave, in which it was fine, but after scattering it will come out in some different wave front nature, and here we have considered this is spherical wave. So psi s, this was plane wave, and the scattered wave will be spherical wave. And the feature of spherical wave is the amplitude will be decaying as 1 by r. So psi s, mod of psi s will decay with 1 by r. So psi s should be e to the power I k r by r, or basically e to the power I k dot r by r. Okay. But look at the setup here. I have put some detector. These are the detectors of this scatter wave, and the detectors is at some distant point from the scattering center. So this D point is very distant point from this scattering center. So after traveling very distant point, this I k dot r will contain the radial component, the transverse component, this r component, theta component, and phi component. But effectively, this will not depend on the theta and phi component. This will only depend on the radial component. So for this assumption, you can write psi is in the order of e to the power I k r by r. Okay. So this was incident wave, typical plane progressive wave, but scattered wave will be spherical wave, and the direction of propagation will be along the radial direction. So only radial component of k will exist. The theta and phi component will not contribute to this phase factor. So psi s should be e to the power I k r. Okay. Another very important point is that the scatter will not be uniform in all directions. Suppose you consider some axis. Okay. Suppose this is scattering center. This is scattering center, and you put some axis along this direction, and this angle is theta. So the scattering along theta direction and scattering along some different phi direction, this will be different. Okay. Because due to the obstruction, the scattering will be the amount of scattering will be different in different direction. So it will depend on theta, but it will not depend on phi, of course, because this is spherically symmetric potential. So if you consider some circle in that way, the scattering in all points of this circle will be same, but for different theta it will be different. Okay, so the scatter wave can be modulated by some modulating factor f, which will be the function of theta only, not depend on phi, not depend on r, not depend on phi. It will depend on theta. Okay, so then the complete wave function psi, you can write it is e to the power I k dot r plus f of theta e to the power I k r. So this is the phenomenological estimation of the wave function of a scattering setup, the wave function of the complete scattering setup. Now, this portion is for incident wave and this portion is for scatter wave. Okay. Okay. Now we have defined already in the corresponding previous class, we have defined the scattering cross sections. We have found the differential scattering cross section d sigma by d omega. That means the amount of scattering per unit solid angle. It is found to be mod of f theta square. And the total scattering cross section sigma, this is f of mod theta whole square of d omega. This total scattering cross section and the differential scattering cross section. Now our primary job in our hand is to estimate this f theta. F theta, here f theta is introduced phenomenologically. Okay. We have considered the modulation or the variation of amount of scattering along different theta value. So we have put some modulating factor, namely f theta here. But f theta is not well defined. It's just a parameter used from our common sense or the phenomenological parameter. F theta is just a phenomenological parameter. And using this estimated or phenomenological choices of wave function, we have found the expression of differential scattering cross section d sigma by d omega and the total scattering cross section, this one. But we have to find the explicit form of this f theta. Okay. You have to find the value for the expression explicitly for this modulating factor f theta, and then you can easily find the differential scattering cross section as well as the total scattering cross section, and you can analyze the features of this scattering through these parameters, because sigma and d sigma by d omega, these are the characteristic parameters which can define or which can examine the features of the scattering. So the whole scattering can be judged, can be examined through these parameters. So we have to find f theta in very explicit form. Okay. And in order to do that, we have to solve the Schrodinger equation. And the Schrodinger equation was minus h cut square by twice m grad square psi plus v of psi is equal to E square. This was very known equations to find the wave function, and this is Schrodinger equation. And this equation can be written like grad square plus a square of psi is equal to twice mv by h cut square of psi, where a square is equal to twice me by h cut square. So that's why I am putting this k square in the place of twice me by h cut square. Then we have found the form of Schrodinger equation as grad square plus a square of psi r equal to okay, grad square plus a square of psi r equals to twice m t of r by h card square of psi r. Now for this setup, we have put the spherically symmetric potential, which is V of r only, and the whole portion, this whole portion I am writing, suppose this is u r, so psi r is from here and the whole thing is constant, so Sm by h cut square is a constant, so this is only function of r, so u r psi. So effectively, you can write the Schrodinger equation, grad square of this one, grad square plus k square of this one is equal to u r of psi. Okay. So it seems like some known partial differential equation. This equation seems to be very special, very familiar and known partial differential equation. This equation seems to be very similar to Helmholtz equation of second kind. Helmholtz equation of second kind. The equation was like grad square plus k square of f of r equals to gr. This is Helmholtz equation of second kind. But this equation is not completely like the Helmholtz equation of second kind because this gr was the known function of r. But here this term is not known. This is unknown function. Why unknown? Because we have to find the explicit form of psi r. Psi r is the solution to be found. But at the right hand side, we will find psi r itself. So the inhomogeneous part is not defined. Okay, so it is not completely the Helmholtz equation of second kind. But for a moment, you can pretend that suppose you can define this one. Okay, if you can pretend this is the known function for the moment, then you can treat it as a Helmholtz equation of second kind. But not in general, this is Helmholtz equation. But for the time, we are considering suppose this is like the Helmholtz equation of second kind. So at first, we have to write the solution for this equation, and the solution, you know, it is complementary function CF, okay, and the particular integral. And particular integral, you know, in terms of the green function, which is g of r prime. Then the inhomogeneous term, which is u of r prime psi of r prime d of r prime. So this is the particular integral. Okay. And what is complementary function? If you put it to be 0, then the solution will yield the complementary function. And effectively, this complementary function is to the power I k dot r. Three particle solution or plane progressive. So at the end, you can write psi r to be to the power I k dot r plus r prime u of r prime r prime d over. Now your second job in hand is to find the green function for this equation. Once you find the green function, then you can find the explicit form of this solution. Okay. So in order to find the green function, you have the equations grad square plus a square of g r prime is equal to the Dirac delta function delta r minus r prime. So now this equation is to be solved. This equation is to be solved in a very particular way. You know the rule in which you can solve this equation. So in order to solve this equation, at first you have to write the solution in terms of Fourier transformation, and then you can solve it. But before that, I am putting the coordinate transformation, let r minus r prime to be r. So then the grad square is basically in terms of the test coordinate grad r square, which will be grad r square. So the grad can be transformed in terms of the new coordinate like that way. And you have the defined natural boundary condition when r tends to infinity. That means your detector is at infinity from the source term. The source term is at the scattering center. Then the green function will vanish. So z tends to 0. Okay. And again, this is for r tends to infinity also. Because if r tends to infinity, then capital R must be infinity. So the boundary conditions and the coordinate transformation, they are compatible to each other. The new coordinate is compatible both with the operators grad r square as well as the boundary condition. So hence you can put g r prime to be z r. G is the function of r and r prime, but explicitly you can write this is depend on in that particular way g r minus r, because these are compatibles. The boundary conditions as well as the operators, they are following this natural result. So g r prime is equal to 0. So again you can put grad r square plus k square of z r equal to delta over r in terms of the Fourier transform. And you can write this is in 3 dimensions 1 by twice pi whole to the power 3 half, and then the triple integration over, suppose this is g tilde, and the Fourier transform, Fourier conjugate coordinate is suppose q. So this is g tilde of q e to the power I q dot r dq. So this is the Fourier transform of GQ. GQ and GR are the mutual Fourier transform. Similarly, you can put the integral form of Dirac delta function, which is q e to the power I q dot r dq. This one. Now you can put all of these things in the equation, and if you look at here, the grad square operator will yield minus I minus iq dot iq, so minus q square. So at the end you will find minus q square plus k square of g tilde q e to the power I q dot r dq into the power 3 half is equal to 1 by twice by whole cube e to the power I q dot r dq. This is delta. Now comparing the equations, left hand side and right hand side, we definitely find z tilde of q is equal to 1 by twice by whole to the power 3 half into 1 by minus q square plus q square. So just for compatibility, I am changing the signs, like minus 1 by twice by whole to the power 3 half 1 by q square minus k square. So this is the Fourier transform of the green function g tilde q. But definitely you have to find zr, not g tilde q. You have to find zr. So zr will be the Fourier transform of g tilde q. So z of r, it is g tilde q to the power I q dot r is, so 1 by twice by whole to the power 3 of course. So you have 1 by twice by whole cube integration e to the power I q dot r by minus q square minus k square, and this is dq q. Actually this is volume element. Dq vector means volume element, which is twice by q twice by q square sin theta d theta d theta. The volume element is defined in that way, twice by q square sin theta d theta d phi, where theta is the polar angle in 3 dimensions. So simplifying this expression, you will find z of r is equal to minus 1 by 4 pi square. 4 pi square. Okay. There will be integration e to the power I q dot r. Okay. Then q square, again q square sin theta d theta dq by q square minus k square. Okay. This one. Now this q dot r, it's a scalar quantity. So luckily this is scalar quantity, and it will be invariant, it will be unchanged under any type of rotation because it's a scalar. So making the rotation of the coordinate system, you can choose the angle between q and r to be theta. That means suppose you are choosing r along z axis. You choose this r along z axis, then the angle between q and r, that means the angle between q and z, which will be polar angle. So q dot r will be q r cos theta. So this was not actually arbitrary, but as the physics does not change, as far as the physics is concerned, they are invariant. The laws of physics or the physical property regarding this transformation will be invariant. So you can make such transformation because this quantity will be invariant. So again, you can write z of r, z of r, green function. Now this truly green. Okay. So g of r is equal to minus 1 by 4 pi square e to the power, sorry, q square e to the power I q r cos theta, then sin theta d theta dq by q square minus r square. At first make the integration about the theta. Okay. The integration limit for q will be from 0 to infinity, and the integration limit of theta will be from 0 to pi, the polar angle. So integrating over theta, if you put cos theta equal to z, then minus sin theta d theta will be dz. So the integration will be very similar, like 1 by 4 pi square integration from 0 to infinity q square by q square minus r square with e to the power minus and minus 1 minus and minus sin theta d theta will go up. So e to the power I qr cos theta, cos pi means minus 1. So e to the power minus I qr minus e to the power I qr by I qr with dq. Okay, this one e to the power minus I qr by e to the power I qr with this one. Um, so then surely z of r is equal to 1 by 4 pi square, 4 pi square of r, this one r. 1 q will be cancelled out, so integration of dq is from 0 to infinity, then uh, q square minus k square, always there. Then this one, so this one is minus twice e to the power I theta minus e to the power minus I theta, which twice I sin theta. Okay, so twice I sin theta, this was minus twice I sin theta. So this is minus twice I sin of here by I. So it will be minus 1 by 4 pi square of r integration 0 to infinity q sin, sorry, sin kr, not kr, this was qr. So this was sin qr. So by q square minus k square. So it's q. So we have to perform this integration, and clearly there is a pole, there is a singularity at q equal to plus minus k. So this integration can only be done through the contour integration. Okay. So it's not a straightforward integration because the function is not analytic. So in order to do that, you have to find the particular contour. And look at here, this is somehow the even function of q, because if you put minus q in the place of q, the function will be identical. So hence you can write this gr to be minus 1 by 8 pi square of r. 1 2 will be divided, then it will be 2, and the limit can be written from minus infinity to plus infinity, because you know for even function 2 into 0 to infinity it will be minus infinity to plus infinity, and then q sine qr by q square minus k square of d. This one. So you have to perform this integration. So explicitly, I have performed this integration or this integration. This integration minus infinity to plus infinity to the power sorry sine qr q. So this is somehow the contour integration of z sine of rz by z square minus k square of dz, and the contour is the half circular semicircular contour. Okay, and the poles or singularity is on the real axis. The singularity is here and here. This is plus k, this is minus k. Okay, so you have to find the residues for these two singularity or 2 points, and then you can integrate this expression by using the Cauchy residue theorem. Okay. So again, I am going to write this one in terms of the exponential way so that you can find the residue very easily. So it will be 1 by 2 integration over z. So 1 by 2i basically 1 by 2i. Then 2i sin z, it will be to the power I z r minus e to the power minus I z r by z square minus k square of d. Okay. So you can write this one as z e to the power I z r by z square minus k square dz minus z e to the power minus I z r by z square minus k square of dz. Okay. So in the both expression, we have two poles at z equal to plus k and z equal to minus k. For this expression, if you put z equals to k, that means the poles at z equals to k, this term will yield into the power I k r. Okay, so I am writing this one. This is very important. Okay, so you have two terms. One term is integration dz into z e to the power I k z by z plus k into z minus k, and another term is dz into z by e to the power minus sorry I z r, okay, by z plus k into z minus k. Okay. Now here you have two poles, z equal to plus k and minus k. They are also the same, z equal to plus k and minus k. Okay. Now if you put z equal to plus k here, then this term will yield e to the power I k r. Okay, and here if you put z equal to minus k, then it will yield e to the power I k r. And this e to the power I k r, it is outgoing spherical wave. Okay, this is outgoing waves e to the power I k r. And the opposite is the incoming spherical wave, because if you put z equal to minus k here and z equal to plus k here, then we will find e to the power minus kr from the both expression. Okay, so here you can choose the contour in two different ways. For spherically outgoing waves or outgoing spherical waves, you can choose only z equal to plus k for this expression and z equal to minus k for this expression. So for this one, first for outgoing wave, that means e to the power ikr, for e to the power ikr, uh, you have to put z equals to k for the first part and z equal to minus k for the second part. So for first part, then you have to choose this one, this contour. Then z equal to minus k will not come into play because this is outside the contour. Okay, z equal to minus k will be outside the contour. Then only z equal to plus k will yield the e to the power I k. It is for the first part, and for the second part, the contour will be like that. Then z equal to minus k will come into play only. Z equal to plus k, it will be outside the contour. Okay. So this is for outgoing wave. On the other hand, if you want to find the incoming spherical wave, then the contour will be alternative. That means this will be for first part and this will be for second part. This is for first part, this is for second part. This is for outgoing wave. For incoming wave, this will be second for second part and this will be for first part. However, in this situation, the scatter wave will always be outgoing. Scatter wave never be incoming scatter wave, because after being incident on the scattering center, it will scatter away from the scattering center. So it will be outgoing spherical wave. So that's why we are concentrating on the outgoing spherical wave. That means plus k for this part and minus k for this part. So the residue for first part. So the first part, the residue is limit z tends to plus k, z minus k of fz. That means z into e to the power irz, irz by z plus k into z minus k. So now you can put the value of k here. So k e to the power ikr by 2k. Okay. So k e to the power ikr by 2k. So this one, epsilon e to the power ikr by 2. So this is for first part, and residue for second part. This will be limit z tends to minus k, okay? Then z minus minus k, that means z plus k into z to the power irz by z plus k into z minus k. So z plus k will be cancelled out. Then it will be minus k e to the power this was minus. So minus k e to the power plus kr plus ikr by minus 2k. So this one will be e to the power ikr by 2. Okay. power I k r by 2 and e to the power I k r by 2. Same way. So that's why you have e to the power I k r twice pi I into e to the power I k r. Okay. So the result will be, the final result Zr will be minus 1 by square of r into 1 by 2i, okay, into twice pi I into e to the power I k r by 2. 2 and 2 will be 1. This is 2, 2, I, 1, 5 will be gone. So, it will be minus 1 by 4 pi r into e to the power I k r. Okay. So, the green function for the Helmotz equation is very clear. Z of r or I k r, right? So, this was in terms of the transformed coordinate. Now, this one, Z of r prime, that will be minus 1 by 4 pi e to the power I k mod of r minus r prime by mod of r minus r. Okay. Now you have to make some approximations for this expression. So, mod of r minus r prime, which will be root over of r minus r prime s square. This will be r square plus r prime square minus twice r dot. So now you can take common as r, which will be 1 minus twice r dot r prime by r square plus r prime square by square. So as r prime is very less than r, because r prime is source coordinate which is very small, and the detector is at infinitely long distance from the scattering center. So this can be taken to be 0. Okay. Now, if you can neglect this term, then you can also neglect this term, because r square is very greater than r prime. Then you can write 1 by r nearly equal to be 1 by r, but not for this phase part. Okay, you can put this one nearly equal to 1 by r. This is no problem, because this is trivial. 1 by r prime is very less than r. But for this phase part, you have to put some non-trivial terms. Otherwise, you will not find any effect of the scattering. So, for the phase part, we are not neglecting this term, but for the 1 by r term, we are neglecting this term. So now, this r minus r prime mod, which is r into 1 minus twice r dot r prime by r square equal to the power half. Yeah. So this is r into 1 minus r prime minus r by r square. So this is r minus r dot r prime by r. Okay. So k into mod of r minus r prime, which is kr minus k into r dot r prime by r. So this is kr minus k of r cap dot r prime. Now k is along the r cap because you are choosing k is equal to only the radial part of t. So k vector is equal to k r cap. So for this situation, you can write this is k dot r cap. Yeah. So you can write this g of r to be e to the power minus 1 by 4 pi of r into e to the power I kr minus k dot r prime. Okay, I kr minus k dot r. So then the solution, the complete solution psi r, it will be e to the power I k dot r, which is the complementary function, plus particular integral. Particular integral will be minus 1 by 4 pi into 1 by r, integration g of r. G of r will be equal to minus 1 by r to the power. The integration will be over r prime, so you can write it to the power I kr by r, then e to the power minus I k dot r prime into u of r prime psi of r prime d of r prime. Okay, after putting the value of green function, you will find this one, and already you know the phenomenological form of psi r, which is e to the power I k dot r plus f of theta e to the power I k r by r. Now comparing these two, you will find f theta. F theta is equal to this one, which is minus 1 by 4 pi integration e to the power minus I k dot r prime, then psi of r prime u of r prime d r prime. Okay. Now this is f theta. But clearly, still it is not well defined because psi r is unknown. At first you have to find psi r prime or psi r, then you will find f theta. Okay, so it is not a solution for f theta, rather it's an integral equation. It is an integral equation for f theta. Okay, so clearly the job is not done. Still the job is not done because you have to find the solution for psi r, then you will find this f theta. That means the parameter which will yield the differential scattering cross section and the total scattering cross section. So in order to do that, you have to follow some advanced mathematical tools, namely the Born approximation method in different orders. Okay. So in the next classes or in a series of next classes, we shall find the approximations, following which you can find some power series terms for f theta, and those terms are namely the Born approximation terms. So following some power, some particular order of Born approximation, you will find this f theta, and you can use this result to analyze some scattering experiments like Rutherford scattering or so on. Okay. So in the next classes, it will be very important to find the explicit function of f theta.